Second keynote of the morning, Fernando is the creator and current lead developer of IPython, a founding member of NumFocus, and a professor at UC Berkeley.
Bonjour, Montréal. Hi. Good morning, everyone. Thanks, first of all, to the organizing committee. This is only my second time in Canada. My previous one was for the 2012 PyCon Canada, which was a great event. And today I want to talk about something that sort of dovetails into what Jessica was saying. She was talking about reaching to the next generation of programmers and members of society who are kids, and I'm talking about the reaching to the scientific community, which is the community that I belong to, and how the Python world has actually, and the open source community have actually had a huge impact in what science is and what science does. The ideals of science that many of you may sort of have a rough sketch of what science is in your head is that we are searching for truths about the world that are verifiable, that are objective, that we validate by reproducing, by building upon the work of others, and which is a collective enterprise of humanity about understanding nature and improving the world. And the reality of science is actually, unfortunately, a little bit different. It's really the pursuit of very highly cited papers in prestigious journals to pad your CV. Validation is basically, can the referees actually get my paper through into the journal? And they didn't actually see my code or my data, and they didn't really do anything with replicating my work. And it's basically, you only have to outrun the bear, remember. So as long as you get funded, it doesn't matter that your colleagues didn't. And open source software is actually a different community, and I sort of lead a double life. I'm an academic scientist, I'm a research scientist at UC Berkeley, but I'm also sort of software developer by night, and fortunately these days by day too. But I've learned a lot from this community, from all of you. And I think I know there's many sort of members from our scientific Python community in the room, and I think we've all learned a lot from you guys. This is a world that is open and collaborative by definition. This community builds its software out in the open on the internet. It's a continuous and public process. There is no big hold everything in secret until you get the big splash press release and the big paper published. The credit is naturally distributed. It's in the commit logs, it's in the mailing lists, it's in the activities that happen in public. Your ideas get reviewed in public, whether it's a PEP, whether it's a pull request on GitHub. It's a process which is reproducible by necessity. You cannot release software and hope to debug what a problem that someone is having halfway around the world unless you have some machinery in place to make sure that when they install it, you have some understanding of what's happening to them. So this is a community that has built both technical tools and practices that make things reproducible by nature. You expose your bugs in public. The problems are tracked publicly and are discussed publicly. And testing is part of the system. It's a mindset of saying, we know we make mistakes, we know software has bugs, so we build testing into the process. And one of my colleagues, Matthew Brett at Berkeley, told me a couple of days ago, he said, you know what, one of the things that really starting to work with open source people taught me is how often I made mistakes in my code. The code I didn't use to test before and that I published paper with was pretty much always wrong unless I tested it. So now it has changed the way I think about my code. And Python for us in the open source world have really had a huge impact both in this broader sense of sort of changing how we approach the work of science, but also more specifically in a technical sense, scientific computing is something that started in the world of floating point number crunching in Fortran in the 50s, but has evolved in different directions. On the one hand, we do increasingly abstract and complex things mathematically, but we also now, it is the business of scientists today to actually talk to hardware, to talk to databases. This morning I was having breakfast with somebody who works in Hawaii and writes control software for the telescopes in Hawaii that acquire data and acquire astronomical images for analysis. I work with colleagues in astronomy at UC Berkeley who write exactly that kind of machinery, very famous astronomers and Nobel laureates who write exactly that kind of software. And Python has been a fantastic tool for the scientific community because precisely it lets us bridge this huge growth where Fortran isn't enough anymore. But it lets us bridge it by reusing and rebuilding upon all of that very high quality Fortran C and C++ code that we still do have to use. A very, very brief history. These slides were given to me last night at 2 in the morning by Travis. But it's a very, very quick history of how the numerical core of the Python world came to be, tracing back to Jim Fulton and Jim Hugan in the 90s, who started what became the numeric library. That library went through a round of renovations called NumArray via Perry Greenfield's leadership at the Hubble Space Telescope team. And eventually in 2005, Travis Oliphant, who many of you know, kind of remerged the numeric and NumArray efforts into what is today the NumPy library. And around 2001, Travis, Eric Jones, who's the founder of Enthought, I hope you're here, Eric. I haven't had a chance to see you yet, and Para Peterson got together and created the SciPy, which is both the SciPy library, but also the SciPy conference and community that has served as an aggregator. And Enthought has played a leading role in basically shepherding that community over the last decade. And that became kind of our space. That became sort of our world. But I want to bring that story back to the last couple of months where something exciting has happened, and it's proof that we can have a very meaningful dialogue with your community and with the Python core team. In February, Nathaniel Smith proposed, who's one of the lead NumPy developers, proposed A at B as a valid operation in the Python syntax, which would mean introducing the at character as a new binary operator to represent matrix multiplication. He wrote a very thorough PEP. He went out to all of the scientific mailing lists for many projects and gathered feedback. And on April 8th, Guido sent a very short one-line email to Python dev saying, I'm now accepting the PEP, so you guys can stop joking around. There was a little bit of a joking thread going on, I guess, and he said, OK, that's it. This is going in. And so thank you. Thank you, Guido, Nathaniel, and everyone who put work into that. And very amazingly, the date of Guido's email was April 8th. By April 10, the issue on the tracker was closed. Benjamin Peterson, in 2 days, basically actually implemented the PEP, which is fantastic. So really, thank you, guys. So for us as scientists, Python gives us a lot. We get, very importantly, separation of concerns. We can dump a lot of work on Python dev, meaning the work on the language, thinking about the compiler, thinking about kind of the syntax of the language. We can have a dialogue about it, but that is mostly their responsibility, and that frees us to do other things. And your community to build XML libraries and web libraries and all kinds of things that we use. It gives us a huge amount of leverage with all those tools. It gives us access and a dialogue with industry. There's a lot of partners from industry who are many of those people in those walls who now there's kind of a natural way of talking to them for us as scientists. And there's also, and I want to emphasize this, a culture and a community, right? The BDFL model, the PSF, the models of these conferences, a lot of these things are in many ways different than science, and I would say that they actually represent those ideals of science that I was talking about earlier, are better represented by a lot of the things that you guys have done. And I certainly have learned a ton from this community and from lurking on Python dev, from kind of seeing how these communities operate. But I hope that I can show you that in the other direction, that it really is a dialogue that goes two ways, that we also contribute. We build tools that have broad impact. I did a quick check with the Debian popcon command, and NumPy is reported as being installed roughly in 58% of Debian installations. That's a lot. It means that the scientists have built a tool that really is an important Python tool, and that benefits many, many packages. It ships now in OS 10 out of the box. Mavericks ships with NumPy and Matplotlib, so you can plot data out of the box in OS 10. And it's not just NumPy. We have a big ecosystem. These are sort of the core packages of the scientific ecosystem. NumPy, SciPy, Matplotlib, SymPy are kind of the base layer of the scientific ecosystem, but we also have tools like scikit-learn and pandas that there have been tutorials about here for machine learning and statistics, NetworkX for graph theory analysis that Matthew Russell uses in his beautiful book, scikit-image for image processing, Cython, which also the core language team is now, I know they've had discussions about. So we have a rich sort of a federated ecosystem of tools that I think are valuable as well. We bring a different community, which means we bring different usage patterns. I've had really great conversations with Nick Coughlin about how the usage patterns and the kinds of ways that we use the language is different, and that actually is valuable because it brings kind of diversity of ideas to the community. And going back to what Jessica was saying, well, many of us scientists are in academia. We teach, we're at universities, which means that we can expand Python's reach, maybe not exactly in the direction that she was talking about, but there is overlap between those communities. For example, UC Berkeley and MIT have recently, in the last couple of years, changed our core CS courses from Scheme to Python, and at Berkeley they actually basically did a little quick rewrite of the SICP book that is Python oriented, and obviously that has draw and that has pull. We have efforts to reach out into the scientific community. The Software Carpentry Project that is hosting, Greg is speaking later today. Titus Brown is here in the room, who's another one of the kind of leaders of that effort. Software Carpentry reaches out to practicing scientists and teaches them how to be better computational people as part of their day-to-day scientific work. I really encourage you guys to engage that. And there's also something that I think shouldn't be discounted, which is that in the last couple of years, something is happening. There's this big data science buzzword, and yes, it is a terrible buzzword, but it's there. And what's interesting about it, this is a plot that I didn't make. This is copied from a blog post that came out looking, and unfortunately the fonts are too small for projecting, but I'm just reusing the image. The lines that go, the red line that is kind of trending down is R. The blue line that's going up is IPython. The green line is Python. These are abstracts at the Strata O'Reilly conference, which is the big business, big industry, data science and big data conference. And it means Python is really playing a role there. And this is because these tools that many of us built for scientific research, all of a sudden are exploding in industry, and people in companies and in industry are realizing that the Python stack for science is actually a great stack for building for working on those kinds of problems. And so I think it gives Python reach and exposure into a side of industry that is potentially going to be a very important problem business-wise. There's also interesting changes in science itself, in the funding. So last year, UC Berkeley, together with UW at NYU, we won a competition as a collaboration for a roughly $38 million grant from the Moore Foundation and the Sloan Foundation to build data science environments, whatever that means, over the next 5 years. And interestingly, in our proposal, in the Berkeley proposal, Python and open source were at the heart of the proposal. And in the MOUs between the three institutions, there's explicit language about open source software coming out of this initiative. This was announced at the White House last November. And at Berkeley, what we did is we actually got the university to fund to create a new institute. It's called the Berkeley Institute for Data Science, BIDS. Right now, we're remodeling the main campus library at Berkeley to house it. Tim O'Reilly and Peter Norvig were our keynote speakers when we launched the announcement there. This is on the lower left, you have a picture of Katie Huff, who's one of the women who lead the scientific Python community. She's one of the chairs of the organizing committee for our conference with Tim O'Reilly during our little poster session. And in the upper right, the person on at the bottom is Saul Perlmutter, who's the Nobel laureate in physics from 2 years ago, who discovered the acceleration of the expansion of the universe, and he's our lead PI, and I've been helping him. If somebody saw my tweet about how to teach a young girl, Python a few months ago, that's because Saul was asking me how to get his kid into Python. And so Python really is basically playing a role at the heart of one of the most ambitious initiatives that we have right now in transforming science. In education, we're seeing, this is Harvard's CS 109 course in data science. All of it, it's all Python. All of the homework sets are these absolutely gorgeous, I don't have time to show them to you in detail, but they're these absolutely gorgeous, extraordinarily elaborate data science problems with theory, with references, with data. If you want to learn sort of really hands-on data science, go through those lectures and do those problem sets. They're absolutely wonderful. We've also learned from the PSF, and several of us who are here in the room got together a couple of years ago and created a foundation with the help and conversations from folks at the PSF called NumFocus, which in many ways plays a role similar to that of the PSF, but in the scientific world. I encourage you guys to go see Leah Silen, who's one of our of the key people in NumFocus, and she's here at the Continuum booth if you want to talk about what we're doing in problems akin to those that the PSF has, but in reaching out to the scientific and academic communities with open source code and bridging between academic research and industry. So This is, I want to switch gears a little bit now from the big picture of open source and science into the one specific project that I've been involved with that Alex mentioned, which was IPython. It began as me trying to procrastinate a little bit on finishing my dissertation and wanting by the way, most of the projects that I showed in that slide that had an icon were somebody's thesis, postdoc, or tenure procrastination project in the scientific community. So us scientists, we have a long and proud tradition of doing that. And IPython is no exception. It began as me trying to get a better shell for Python. Python has an interactive shell, but it's fairly limited, and I wanted something a little bit better. At the beginning, it was a 259-line script that basically just hacked into changing the input and output prompts and added output caching to the prompt and loaded numerical and plotting libraries, etc. 13 years later, I thought it was going to be just an afternoon hack. That's what I told my advisor. It's been 13 years, and now we have about 150,000 lines of code, over 15,000 commits, over 300 contributors, 6 languages now. There's a lot of JavaScript in there. And it's obviously not my work. I really want to stop for a second and emphasize that everything that I'm going to show is really the output of a very talented team. Brian Granger is my co-PI. He's a physics professor at Cal Poly in San Luis Obispo. Min is our lead engineer. He got his PhD in plasma physics at UC Berkeley, and he now works there full-time. The people who are bold-faced in that slide are simply bold-faced because they are full-time developers. We now have enough funding to have 6 of us working full-time. And Matthias Buissonnier, who's at the top right, is actually here in the room. He's the only core developer who is here. But they are all really the ones who do all the hard work. I don't, so I'm taking credit for somebody else's work at this point. We have funding that we are very grateful for. The Alfred P. Sloan Foundation funds the bulk of these salaries, but Microsoft Research has made important donations to the project that we're grateful for. And Rackspace, I know you guys are here. Thanks a lot because you guys support both in services, and Kyle Kelly, who has become a core developer, are supported by Rackspace. And so how did we go from 250 lines of code to 150,000 if all we do is basically exec your source and user dict? What we do is basically, we've created a lot of stuff around language-independent tools for what happens at the shell, but in an abstracted fashion. I'm going to show you examples of that. The simplest way that I can describe it quickly is that we've basically created a protocol for interactive systems to talk to programming languages. So you can think of it sort of like an HTTP-style protocol, but for interactive computing. And we also have a format for storing those interactions, sort of like HTML, but it's actually a JSON data structure. At the protocol level, we provide, when you install IPython, we provide one kernel, one of these interactive kernels. It's the IPython kernel. What used to happen just at the shell, it now happens over the network. We provide 3 clients, the same terminal client if you've ever used IPython, but also a graphical Qt console client and a web notebook. This is being presented in the web notebook. There's a format. The format, there's an API for converting those notebooks into other forms of output, and that's going to be important, as we'll see in a minute. We have a notebook sharing service called NBViewer, which is hosted by Rackspace, as I mentioned. And we also have a library for high-level parallel computing that takes a lot of the ideas from multiprocessing and concurrent futures, but presents them in a way that is a little bit more amenable for the kinds of things that we want to do in science. So it does execute code, and what does it do? Well, if you simply import some, and you load a data set and you hit enter, you can get plots. This is actual code where we're plotting with Matplotlib. And it's plotting with Matplotlib, but it's actually using D3 to do the rendering. So 2 lines of code will let you load a data file and visualize it quickly. We don't have to envy always R for being able to do that. But in addition to executing Python code, we can mix and match with other languages. So this is, and I apologize if it's a little small for you guys to see the code in the very back of the room, but suffice it to say that what we're doing here is executing inside of the Python process, loading a Julia interpreter. Julia is a new language out of MIT for numerical computing, and the next block is now Julia code, which is making callbacks to Python code and producing a plot by mixing and matching Julia syntax with Python syntax to generate a figure using Matplotlib from an internally loaded Julia interpreter. And, but the integration between the languages goes pretty deep. In Julia, we created this figure, and we pull it out and display it as a Python variable, and we can keep modifying it afterwards as a Python data structure. You can even mix and match at the level of having the call stack be completely intermingled. So this is an example of writing the classic Fibonacci little example from the Python tutorial, but as a two-step recursion instead of a one-step recursion, where now one version of Fibonacci is written in Julia and the other one is written in Python, and when you call the outer entry point, it's switching back and forth between the two, and you can see how the two-step recursion stack unfolds in there. So these are the kinds of things that we can sort of do cleanly with the IPython kernel. We can, as I said, we can load data and look at it. Let's imagine that I have an image with, in this case, some random values, and I'm plotting it, and I'd like to know, well, where are the higher values? I can obviously start thresholding this image and looking at it and playing with a threshold to see where important values. In this case, it's random noise, but normally you do these kinds of things with real data. But this is the kind of thing where it's very useful to be able to have interactive controls. And so we've added the ability to simply grab, say, the plotting call that shows the image thresholded at a value, and simply say, I want that, but I want it interactively with a slider that goes between 2 and 2, and by simply writing that, by simply saying I want to interact with that, I automatically get a slider, which allows me to change the image threshold, and whenever I move that slider, it's simply calling back into the kernel from the JavaScript side, calling back into the kernel, re-executing the code, and letting me, so I don't know how to write GUI code, and I joke that I'm already old enough that I'm going to die without writing ever GUI code, but it is useful to have interactive controls for parameter exploration often, and being able to write just one line of code and saying, I want to interact with a threshold argument is extremely, extremely useful. And certainly for us in scientific work where we often have to play with parameters, being able to do this kind of thing easily is very nice. And now that we have this connection between what happens in the web browser and what happens in the back end, we can build things like spreadsheets, but where the nice aspect that I like about spreadsheets is being able to manipulate the data entry aspect. I don't like the fact that they blend in data input and output. So this is a toy example again, but to show the kinds of things that become possible. Here I'm loading a data frame, a pandas data frame that in this case has random numbers, and that's what it looks like when I print it. And if I simply call in the edit function, this is a little JavaScript table where I can now go in and edit. And when I look at it again, the edited values have changed. So basically, I can have an editable data structure right in my notebook where I can make the data transformations, but I'm still doing the visualization with normal code. So I can mix and match the things that are natural to do with hand interactivity, such as in a spreadsheet data manipulations, but leaving the computational part to explicit code, which means I can unit test that, I can run it against a validation suite, I can reuse it with other forms of input if I want to. We've actually gone, this interaction between, this ability to interact between the web browser and JavaScript and the back end goes fairly deep. So this is an example of writing a little bit of code that uses D3 to simply factorize a number, and as it's factoring the number, it's sending data to the D3 to a D3 graph-directed layout, and I can say, well, if I want to illustrate, I know 72 has a lot of factors, so if I want to illustrate how does factorization work, I can run this. It's sending data to D3, and D3's event handlers are responding in real time to the Python kernel, which is sending it data, and they're updating. I don't have callback event handlers wired in here, but D3 could also send callbacks back, and maybe based on the node you click, stop factorizing that particular branch or something. So these are obviously toy examples, but they're there to illustrate that we've really built an infrastructure that lets us get really wire back potentially very sophisticated computational services into the environment of the web browser. This happens to be running locally on my laptop, but that code could be running on an arbitrarily large backend that is attached to a huge data center to a supercomputer, and we've done that, but that is still rendering in your notebook. All of this is based on a fairly simple architecture where the kernel executes codes, sends messages over 0MQ, and clients listen to those messages. And as I said, we ship a terminal, a Qt, and a web console, but people can write other clients, and as we'll see in a minute, they have. But people have also written other kernels. They've written kernels in many languages now. In particular, we're excited about the fact that we now have a kernel in R. And it's really great because the R kernel lets you do things like this. So when we have an R kernel, this is now using pure R syntax. This is R syntax. This is not Python syntax. And it's loading a library for mapping that is apparently very popular in the R world. And so if you happen to need to use pure R, we have an R kernel. We have a pure Julia kernel. As I showed in the previous slide, we're now up to something like 11, 10 functional ones, and yesterday somebody tweeted that they were working on an Erlang one. This architecture is based, can be exposed not only as a notebook. You can create your own web services. So this is an example. This is an example of a non-notebook looking interface where I still have event handlers, but there's no code to type. All I have is my own web service that calls back to a Python kernel and reuses 100% of our code, but presents a different web interface. So if you don't need a notebook document style thing, but what you want is a web service that attaches to the back, you can just reuse the JavaScript libraries and you can reuse all the communication protocol machinery, but you don't have to expose it in necessarily the same way if that doesn't make sense in your application. And so around this, with this infrastructure, what we're seeing is an ecosystem of tools growing. For us, as I said, obviously we are scientists, that's what pays the bills. So we're trying to use this to do better research and to do research that is reproducible. This is an example of a paper we published last year. This is one of the Nature journals, in this case in microbial ecology. And this was a collaboration with biologists. I'm not a biologist, where we did we ran some code on an Amazon cluster, parallelizing using the IPython parallel as a genomics analysis. And in one day, we were able to go from a serial script that would have taken about a month to run to a result that same afternoon, we called the editor of this Nature journal and asked if we could submit a rapid communication paper for that, because we had a publishable result by the end of that afternoon. But what we did was, in addition to publishing a paper, which is, as I said, what pads the CVs, we actually tried to do something a little better, which was to publish the virtual machine images that we used to do this work. And this was following on the steps of Titus Brown, and I know Titus is in the room, who had already done this with one of his papers, which is to make available the entirety of our computation in the form of an Amazon machine image. So all you have to do if you want to replicate our work is to copy that config file that tells you which Amazon machine image to instantiate, and then you can effectively replicate exactly our computation, and then begin exploring maybe the parameter space, ask if we made an incorrect statistical assumption, etc. Obviously, you have to pay your Amazon bill, but the machine image is there with all the code and data to do it. And so we're trying to show that it really is possible to do computation and communication about computing that is more reproducible. People are using this for technical blogging. So this is an example of Jake van der Plas, who is also here. He was teaching yesterday, whose blog, this is his blog, but his blog, which is a beautiful Python blog, every blog post he makes is a Python notebook. So if you want to have a conversation about something he's saying, you don't have to argue in a vacuum whether he did something right or not. You can just basically download the blog post and run it yourself, and go down to the commenting section and have a more informed discussion. And he's written a Pelican plugin to make it very easy. My blog is also the same way. We're also seeing books, not just papers, but entire books being published in this way. So a colleague of ours, Jose Unpinco, wrote a book on Python for signal processing, where the whole book was created as notebooks. And he publishes not only the hardcover, expensive, glossy paper Springer book, but also a Git repo on GitHub, where you can download and execute the entire book. O'Reilly has a book called Mining the Social Web, and I know the author, Matthew Russell, was teaching a workshop here. The book wasn't written has notebooks, but it has a collection of notebooks for all the examples in the book. So again, you don't have to wonder whether the author copy-pasted the right thing or whether they changed the script at the last minute and they didn't update the book, because all of the results are actually executable. And a lot of this is based on, it takes advantage of a tool that Matthias Buissonnier, who's here in the room, wrote in 2012 called the Notebook Viewer, and which allows you to paste. If you want to give a notebook to somebody and you want them to be able to read it without installing anything, all you have to do is paste in here the URL or the GIST ID of that notebook, and we will render it for you. So this is an example of a Julia notebook. If I click on that, what you see is this. This is a web page. This is just my web browser. I can't execute anything here. This is not code. This is just an HTML page. But I can go ahead and download it. If I click on this, my browser will download that notebook. So we make sharing work as easy as put it somewhere online and send your colleague the URL. They can view it as a web page, and at least they can read the analysis. If later they want to execute it, that's fine. They can do that. But at least we make it very, very easy for them to see what you're doing. And we see traffic on Twitter constantly where people are sharing their work in this way. And I want to take a case study that we saw happen last week, precisely based on this. So 538.com, which is Nate Silver's new data-driven journalism gig, published an article about an analysis of gender in movies, gender and funding, statistical analysis of gender and funding in the Hollywood industry. I'm not going to go into discussing the details of the article. What I want to show is this was what 538 published a couple of weeks ago. So this is actually the 538 website in an iframe. And Brian Keegan, who is a postdoc at Northwestern, he's a social scientist who does network analysis, said, well, I wonder about those conclusions. So he went ahead and said, I'm going to replicate that, but I'm going to do it in the open. So he wrote this and posted it on GitHub and posted a link on NBViewer to NBViewer, which is this incredibly detailed, let me close this down here, it's this incredibly detailed notebook analyzing and replicating and critiquing the results, loading the data, scraping websites, scraping IMDb, running all the code, doing statistical analysis. It goes on and on and on and on. And then you have plots, you have all of the... So it's this extraordinarily in-depth and detailed critique of 538's analysis. They hadn't published their code, right? So he went and posted this notebook, and to their credit, 2 days later, 538 replied, and I'm only quoting a short excerpt of their reply. They said, Keegan made a point. 538 and similar sites should make their data available. We couldn't agree more. And they put up their code and data, in their case it was in R, on a repository on GitHub. So we're seeing in this case a social scientist basically saying, we can do this better. We can take the mentality of the open source community and make this stuff openly available, and actually changing within 2 days the behavior of a site like 538. Others are building. Many others are building atop IPython, both open source and commercial projects. Enthought, who, as I said, has been a supporter of ours since the very beginning. They were the ones who funded the work that led Brian and I to be able to create all of this protocol architecture early on for their Canopy project, which embeds IPython in a console here. Continuum Analytics, which is also here, hosts a version of the notebook online, so that you can, without installing anything, you can go and use it online. It's called Wakari. It's basically an embedded notebook. Microsoft, the team at Python Tools for Visual Studio from Microsoft, just put out. This is a screenshot from a blog they posted 2 days ago. They had already a version that integrated IPython, but they continue to improve the integration between IPython and the Python Tools for Visual Studio plugin. And one interesting thing about this is that when we first met with them, we only showed them where the Qt console code was in our repo. We never actually have seen their code. All they saw was, okay, this is the page that describes the messaging protocol, and this is where the Qt code does it. Okay, we'll take that. And Dino and Sharok went home, and I don't know, a year later they came back, and there was a plugin for Visual Studio that implemented the protocol, and they continue working on that. We've also worked with them on making it very easy to deploy on the Azure Cloud Service, not just just on Amazon. If you are on Amazon, there's an open source project out of MIT called StarCluster. This is what we use for that biology paper that lets you spin up an IPython parallel cluster with a notebook front end by just copying that one config file, basically, for StarCluster. It's a beautiful open source project. The only thing you have to put is your Amazon ID, because obviously you have to pay for the service. We saw last year at SciPy a great talk from the IBM Watson team, not the people who did the Jeopardy contest, but the team that actually is tasked with turning Watson into a product. And this team replaced an existing Hadoop, Java, JavaScript D3 clunky infrastructure that had a slow turnaround time because it was all batchy Hadoop and was very complex to deploy, with an IPython cluster running in parallel and a notebook interface for the engineers to log in. And they went from about 8,000 lines of Java, HTML, D3, and a complicated deployment system to an interactive zero deployment, log in through the web browser, write your code. Turnaround interactive time went from 2 minutes to 2 seconds because it's all done in memory with the IPython parallel stuff. And then when you're done, you save and you send the business person just the link to the notebook, and they can just view your report. You're done. This was again something that the IBM Watson team did without our involvement at all. They found the project and they used it. This was in July of last year, and I was very happy when I saw in November that they turned it into that Watson is now like a $1.5 billion business unit at Microsoft. So it's obviously something that is being used for serious projects. A startup from Boston, a bunch of astrophysicists created an environment for writing collaboratively academic publications, sort of Google Docs style, but for academic writing, called Authorea. And you can write using IPython notebooks right in the environment. So you can collaborate on LaTeX-style academic writing using IPython in the cloud, thanks to the machinery that these guys have built. Another scientifically oriented startup also they're now in Boston, called Plotly, that lets you load their libraries and plot, but it's actually hosting the plots on their servers so that the code and data are available there, and you have a unique URL for their plots. But this is all interactive. I think they're using well, actually I don't remember if they're using D3 or not. But when you run that code, you get a plot embedded into your plot window that has a static UUID referring to the code and data that you can share with others. But it fully integrates with IPython, and we've been working with them on this. We also have a project that came out of the University of Toronto, and one of the leads of this project is here, Tavish Armstrong, called NBDiff. They've been supervised by Software Carpentry's Greg Wilson, that lets you diff and merge notebooks. It turns out these files are JSON data structures, so they're kind of a pain in the neck. If you diff them just with a raw text diff, they're horrible. So these guys are building a web service to give you kind of civilized, structured diffing and merging for these documents. And so this just told me that I'm out of time, but that's good because I am wrapping up. So I want to kind of go back to the two kind of main directions. One is that Python and science, it was interesting to see Brett Cannon on the first morning said that he came for the language, but he stayed for the community, because I looked back at my last slide at PyCon Canada in 2012, and I had that exact same quote 2 years ago, because that is also true for me. I got sucked in when I was a grad student looking for something to procrastinate on, because the language just was awesome. I had written a lot of Perl code for managing my data, and when I realized that 24 hours after having read just the Python tutorial, the standard official one in the docs, I could do in Python things that it's not that I didn't know how to do them in Perl, I didn't know if they were possible in Perl. And I had written a ton of Perl code, so at that point I said, okay, this is what I'm doing. But it's easy to say that when you're a grad student looking for something to do other than finishing your dissertation. It's harder to keep that as a career. And what has kept me in is the fantastic community, both in our SciPy world, which is an amazing crowd, and this larger open source Python community that I've come to meet. On the IPython side, I hope that I've shown you that we've built something that, by having open protocols and open formats, is a useful tool for computing in a very broad sense, and it's not a scientifically oriented only tool. Yes, we build it because we need it, but we hope it's a tool that can be relevant to many of you, and there's a lot to contribute in IPython. There's many projects that need help, and obviously you should work on what really interests you, but if you want to work on IPython, there's plenty of room. And finally, I want to close by thanking, first of all, Guido for creating this fantastic tool and for being open to conversations like PEP 465, which is only the last one. There's been other similar ones in the past, and the entire Python dev team, and also to Diana and Dave Walliver, Diana Clark and Dave Walliver, who have done an amazing job, as well as the local Python organizing team. Thank you very, very much. And I don't know I think we're out of time, but I'm happy to take questions, one or two now, or out in the hall. I'll be here for the rest of the conference.